let's look at some differential calculus. So before you get all worked up about how crazy this word, sort of a term, differential calculus sounds, let's just take a step back and think about where this whole thing comes back from. So earlier on, when you've been working with now analytical geometry and straight lines, you've learned about the gradient or average gradient formula, right? Which is the inclination between any 2 points, point 1 and 2, let's say for example, and the gradient between these 2 points can be given by the formula m is equal to my change in y over my change in x. And that gives us the average rate of change between any 2 points. And it's worked beautifully thus far, because every time you've gotten an analytical geometry question, you've nailed it 10 out of 10. But now things get a little bit more complicated. Not everything in life is a beautiful linear function. A lot of functions in life are curvaceous and sort of go up and down and all sorts of ways. So now let's imagine we had a function or a curve that looked like that. And I wanted to know what the sort of rate of change at any point was. So far, using the methods we know, we would have to pick a point on one end, pick a point on the other end, and find the instantaneous rate of change or the average rate of change. But that doesn't really work quite well, because the gradient would give us the average gradient between this point 1 and that point 2 there, which would map out a gradient that looks like that. And it doesn't tell us exactly what's happening in between here, because this gradient doesn't match the gradient there or anywhere else. So we find ourselves in a bit of a dilemma. But then someone says, okay, but wait, what if I pick points closer to the point I'm looking for? So let's say I was looking for the gradient at this point there. Then why don't I just pick points just on either side of that point? So I'll pick a point over here and a point over there, name this 1 and point 2, and I'll get my gradient for there. But still, again, that gradient is the gradient, which is an average gradient between the 2 points. It's not the instantaneous gradient at that point. Okay, then someone says, in a very smart and clever way, well then, let's pick this 1 point as our point 1 and point 2. That way, it is the gradient at that sort of exact point. Well then, we go back to our formula, change in y over change in x. What's our change in y? Since this point has one y value, my y1 and y2 are the same, meaning my change in y becomes 0. My change in x, this point has the same x value and the same x2 value. My change in x becomes 0. My change in y over change in x becomes 0 over 0. And as the story goes, whenever you divide by 0, you create a massive wormhole, the world gets sucked in, and then we all die. It's not that bad, I promise. Anyway, this is the point where you get to introduce now the concept of a limit. You might be asking, what is a limit? A limit is simply a barrier, a point you cannot get beyond. So let's think of this instance. What is the limit as I walk towards the wall behind this board? The limit is the board. I cannot get beyond the board. What is the limit as this pen tries to fall to the center of the earth? The limit is the floor. The pen, or this marker rather, would fall and hit the ground, and it cannot go any further because that floor right here is my limit. Okay? So now let's take that into our functions. And I say, and I'll show you the new notation I'm going to deal with. And I say the limit as x tends to 3 of a function 2x minus 1. So the best way to evaluate a limit is to see what happens at that limit, what happens at that particular point. So we say, okay, well, what happens when x is 3? So you say 2 times 3, which gives us 6, minus 1, so we get an answer of 5. So basically, when x is 3, my answer is 5. Therefore, as this function, right, and the x value tends towards 3, my whole function will tend towards 5. Meaning, the limit of this function as x tends towards 3 will be 5. I'll go towards 5, closer and closer and closer, and like asymptotically basically, but I'll never get to the number 5. And that's basically how we deal with limits. Now, let's keep that in mind, and then I'm going to go back to my average gradient for 2 seconds. So now let's take back our function. Now we realize that to get our instantaneous gradient, we need to deal with the gradient at a single point. But this formula we've been dealing with only works with 2 points. How do we then take 2 points and make them 1 point? without the 1 point staying 1 point. Sounds confusing, but stick with me. Now if I take a point here, 1, and a point there, 2, and I'm trying to figure out the instantaneous gradient at an arbitrary point here, let's call that C. What I would do is I would bring point 1 and 2 closer and closer and closer and closer together, such that there's only one infinitesimally small little piece in between them, being point C. In that way, the average gradient between 1 and 2 has to be the instantaneous gradient of point C. Okay, how do you put that mathematically? Let's now look at this as though it were a nice beautiful function. So now this point 1 would have an x value, let's call that x1. Point 2 would have an x value, let's call that x2. Point 1 would have a y value, let's call that y1. Point 2 would have a y value, let's call that y2. According to our formula, the gradient between point 1 and 2 is simply going to be my m is equal to y2 minus y1 over x2 minus x1. That's nothing new. It's what we've been doing this entire time. And what's new, you ask? Give it 2 seconds. So now, what I said was, let's bring these points so close together that there's only like one point in between them, and that point will be C. So then I'm going to say, okay, I'm going to say the distance between x1 and x2, and I'm going to define that distance as h. So then I can rewrite x2. x2 can then be written as x1 plus h, which makes sense. If x1 was like the point 3 and x2 was the point 4, my h is 1. Therefore, x2 is going to be 3 plus 1, which gives us 4. That makes sense? Fantastic. Now let's rename our y values and actually put them as functions of x. So that if this is now point x, let's change the 1 to just x. If this was point x, the y value will be the function of x. Make sense? If this point is x plus h, the y value will be the function of, you guessed it, x plus h. Now, let's take this back into our equation for my average gradient. So then my average gradient, let's call it m average, equals my y2, which is this f of x plus h, minus my y1, which is simply f of x, divided by my x2, which is x plus h, minus x1, which is simply my x. Notice how I've got x plus h minus x. The two x's basically will fall away, and I'm left with just the h at the bottom. Starting to look more and more familiar, isn't it? I know, and you're saying it's really easy. So now, the problem is this is still our average gradient because we still have this value of h. But what did I say? Let's let this distance between my 2 points become so small, it's basically nothing. To the point where I have a distance between my points that isn't really a distance. So let's let h tend towards 0. That way, I still got 2 points, but they're so close together, you could basically call them 1 point. So now, to get my now instantaneous gradient, my exact gradient at any point, I can drop the average simply by applying the limit and say my gradient is going to be the limit of that entire function as my h, which is the distance between these 2 points, tends towards 0. So when the distance becomes 0, I will have my instantaneous gradient. So of the function f of x plus h minus f of x, all divided by h. And this beauty right here at the bottom is what we call the first principles equation. And this equation here helps us find the instantaneous gradient of any curve when h tends towards 0. And we can use this to find gradients, instantaneous rates of change, and all sorts of things that you will see when we go about doing examples next.